Well, welcome back to Math 221, everyone. We're going to get started on our last lecture before the exam. Today we're going to be talking about uh, implicit differentiation and related rates in our first part, and then in our second part, we're going to look at just another way that we can use derivatives to help us understand a function's behavior. Um, but before we do that, I want to sort of ask you a question, right? So far we've looking at derivatives of only things that have a behavior like this, right? Of y equals f of x, right? We've taken the derivatives of functions, and that does make sense, right? We talked about it as a thing that you would do on functions. Um, But I think we can expand it a little bit more, right? Because all of our equations, right, and any equation in the variable x and y, right, say something like, x squared y plus y minus x squared plus 1 equals 0, right? This equation, it has some graph in the plane, right? And so our sort of natural question to ask would be, like, what is dy dx, right? What is the derivative? Like, is there a way for us to understand the derivative of this equation, right? The slopes of tangent lines and all of those things, right? And with this one's case, we can solve this for y, right? What we can do is we can, factor y out of this and move that over, right? So we're going to get y times x squared plus 1 is equal to x squared minus 1, right? And then we can divide by x squared plus 1 and get that this is, a way to write y as a function of x. And then from here, you would use, the quotient rule to take your derivative, okay? But what happens when we look at something a little bit more complicated? Say y cubed minus y plus 2x cubed minus x equals 8. Something like this. Now, if you placed a bunch of restrictions on the values x and y could take, you could absolutely, theoretically at least, write this as, y equals some function of x. But in practice, that would be very, very difficult, right? This is what's called an implicit relationship, right? And an implicit expression, right? As opposed to something like this, right? This is an explicit function, right? You're telling me exactly what y is in terms of x, and here you're saying values of x and y solve this equation, okay? But we can use a tool called implicit differentiation in order to calculate something like dy dx for this guy. But in order to do that, let's take a look at a simpler example, right? Let's say y squared equals x, right? And we're asking what is dy dx, right? And okay, well, in order to do this, right, we would want to take the derivative of both sides, right? So, you would look at d dx of y squared is still equal to d dx of x. How can we understand this? The key insight here, right, the key sort of shift in perspective that we want is precisely what we, sort of said when we were looking at this, that with the suitable restrictions, y is a function of x, right? So that means that this is the same as writing d dx of some function, whatever it is, f of x squared. And that's still equal to d dx of x. But once we do this, we can use our chain rule, right? This is going to be 2 times f of x, right, times f prime of x. But f of x is y, right? This is y, and so that means that this is dy dx, okay? So this tells us that 2y dy dx is d dx of x, which is 1, or dy dx is 1 over 2y, right? This is how you can do this, right? A piece of notation, some books do this, some books don't. Your book writes dy dx for all of these, and that, of course, is a totally valid way to do it. The other way that looks a little bit cleaner in my mind, but it's a little bit easier to sort of mix things up, is to write dy dx as something like y prime. Okay, we'll do that in the next example, and then you can make the decision for yourself, the easier way to write it. Okay, but let's turn our attention back to that first one, right? Y cubed minus y plus 2x cubed minus x equals 8. And we want to take the derivative of this, right? Because we want to calculate dy dx, okay? And so as we sort of look at this, this derivative is going to break over the sum. So we're going to get the derivative with respect to x of y cubed minus the derivative with respect to x of y plus, and I'll write just this as 2x cubed minus x because we know how to take that derivative, and then the derivative of 8 is 0, right? But we can follow the same idea, right? We can treat y as some generic function of x. So d dx of y cubed is going to be 3y squared y prime, right? Minus d dx of y, using once again our chain rule here, right? This is just going to come out to y prime. And then plus, it looks like 6x squared minus 1 equals 0, right? And then from here, we can factor out this y prime, and we're going to get y prime times 3y squared minus 1 equals 1 minus 6x squared, or y prime is 1 minus 6x squared over 3y squared minus 1. Again, once you shift your perspective to realize that, again, given the correct restrictions of domain, right, whatever they are, y is just a function of x, and so we can use the chain rule, right? Okay, let's take a look at another one. All right, let's find the tangent line to, say, x squared. Just write it up here. X squared plus y squared equals 4 at 1 square root of 3. So what we want to do here, right, is we need to take the derivative of this. And so if we want to take the derivative of this, right, we need to once again use this process of implicit differentiation, right? D dx of 4. The derivative of 4, of course, is just going to be 0. As this splits across, we're going to get 2x, right? It's going to be plus 2y y prime equals 0. Solving for y prime, we're going to get that y prime, well, if I move that 2x over, and then I have to divide by 2y, and then those two cancel, so we get minus x over y, right? And then, of course, we have to think about our domain restrictions. Well, of course, this would mean that y cannot equal 0. And that would make sense, right, if you think about what this is, right? For those of you who don't remember your conic sections, that's absolutely okay. X squared plus y squared equals 4 is a circle with radius 2, right? So that means when y equals 0, we're talking about these 2 points, which are going to have a vertical tangent line. So of course our derivative wouldn't exist, right? But we want to find the tangent line to this point. So that would mean we would need the slope. But look at this, we know that y prime, which is our slope, is just governed by this, right? So what I can do is I can take dy dx, right? And if I want to plug in 1, 3, there's this fancy notation where you drop a vertical line, right? So 1 comma the square root of 3, right? That just means plug in this point for whatever this is, right? That's minus x over y evaluated at 1 comma the square root of 3, which means it's minus 1 over the square root of 3. And then, using our standard point slope form, since we know the slope is minus 1 over the square root of 3, we would know that an equation for this line is y minus the square root of 3 is 1 over the square root of 3 times x minus 1, okay? Not too terribly complicated, okay? We'll do one more before moving on to this concept of related rates. And that's actually looking for the second derivative, right? What's the second derivative? So we want to find the second derivative of y if our values of x and y satisfy xy minus y cubed equals 4, right? Now, you can't exactly talk about the second derivative of this equation, right? Because an equation doesn't have a derivative. But you can look for d squared y over dx squared, right? Or in this case, y double prime, if x and y have this relationship. Hopefully that distinction makes sense. But what we can do, right, is we can start by first looking for y prime. So we can take our derivative of xy minus y cubed equals 4. Right? We're going to need to take the product rule for this first one, right? So it's going to be x d dx of y plus y d dx of x is just 1, right? Minus d dx of y cubed, and that just equals 0, right? d dx of y is just dy dx, right? So that's going to be x times y prime plus y minus, we're going to get 3y squared y prime equals 0. So what this means is I can fairly quickly, right, solve for y prime. When I factor out this y prime, right, we're going to get y prime times x minus 3y squared equals minus y, or y prime equals y over 3y squared minus x, right, where I took a negative out of this to flip the order and cancel with that negative, okay? Now in order to find our next derivative, right, now that we have an expression for y prime, it's super easy. We just take another derivative, right? So what I'm going to do is actually copy this one, paste it here, and we get that y double prime. Now we just need to use the quotient rule, right? Right, so that means that we're going to do low d high is just y prime minus high d low, right? But what's d low going to be? The derivative of 3y squared is going to be 6y y prime. the derivative of x is just 1, and then we want to divide all of this by 3y squared minus x, okay? And now we want to start to simplify, right? We can actually distribute in this y and give us something like this, right? And then let's rewrite that, right? With 3y squared minus x times y prime minus 6y squared y prime plus y all over 3y squared minus x, and that should be squared, right? But what I can do is I can now factor a y prime out of that, right? So we're going to have y prime 3y squared minus x minus 6y squared plus y. But of course we can simplify this further, right? Because these 3y squareds and then this is just going to give us a total of minus 3y squareds, right? Then so what I want to do next, right, is I actually want to substitute in the value of y prime that I know, right? That's this. It's going to be y times, and I'm actually going to factor out a negative 1 here, right, and get x plus 3y squared over 3y squared minus x plus y over 3y squared minus x. Okay, I'm going to put this on the next page as we continue to simplify it, right? One of the maybe not so fun parts, but one of the common parts, right, of sort of finding these implicit derivatives is, trying to, simplify and break this down into its simplest form. What I'm going to do here, right, is I'm going to write this y with this denominator, right? So I'm going to multiply that by 3y squared minus x over 3y squared minus x. That's going to make me able to take this derivative down to the bottom. We're going to get y double prime, and look how quickly this actually cleans up. We have minus yx minus 3y cubed plus 3y cubed minus xy over 3y squared minus x. It was squared there, now it's cubed. Look at this, these two are going to cancel, and we actually get the very, very nice minus 2xy over 3y squared minus x squared, right? The formula is actually much nicer than one would think, okay? And there are a lot of different ways to sort of march your way through this algebra. I just went with the way that sort of seemed obvious to me. There's a number of different ways to, manipulate it from here through to here, okay? We're going to switch gears a little bit here and sort of start to talk about something called related rates, okay? And related rates builds off of implicit differentiation, and it sort of asks the question of you to consider what happens when, say, both x and y are functions of some third variable, right? So here's the example that actually was taught to me, right, when I was first taking calculus, okay? Say you're blowing up a balloon, right? And this balloon is, perfectly spherical, right? The radius is changing, and so is the volume, right? The rate at which the radius is changing is related to the rate at which the volume is changing, right? Same with the surface area. But both of those are actually changing with time. So here's our situation, right? Again, we have some perfectly, right? We have some perfectly spherical balloon, right? And we're inflating it, right? So it's going to be growing, right? Growing slowly with time, okay? So we know, right, the volume, which is a function of time, right? The speed at which we're blowing, right? The volume is a function of time. Well, we don't necessarily know it. But we do know, and you don't necessarily have to have this, memorized off the top of your head, but the volume of a sphere is 4/3 pi r cubed, right? But like I said, our radius is a function of time as well. But it would be helpful to know, maybe like what is the relationship between dv dt and dr dt, right? And we can calculate that using these implicit derivatives, right? Because when you're doing related rates problems, all of your variables in your expression are treated equally because you're taking derivatives with respect to some third variable, right? When you're doing these problems in practice, you would just write this, right? 4/3 pi r cubed. But then again, what happens when I want to take ddt of this? Well, dv dt is just dv dt. 4/3 times pi is, well, a constant, and we can use this sort of chain rule trick here, right? We're going to get 3 r squared dr dt. Or, if you prefer, right, v prime equals just 4, right, because those 3's cancel, pi r squared r prime, right? This is the relationship between the rate at which the volume changes and the radius changes, right? You could, make a similar argument, right, for the surface area, right? The surface of a the surface area, rather, of a sphere is 4 pi r squared, right? It's 4 times its sort of shadow, which is interesting. But you could actually, follow the same thing on this, right? Take, the derivative with respect to time on this, and you can actually get an expression for how the surface area changes when the volume changes, right? And that's just sort of, a kind of little nifty trick that related rates allows us to do, right? And of course, we can look at something a little bit more practical, I guess, right? Something where these quantities would actually matter, right? Say you have a situation like this, right? Say you have some passenger ship and some oil tanker, right? Say they're leaving port together, right? At the same time, okay? The passenger ship is heading north. The tanker is heading east. Okay, so let's draw a little picture of this, right? So this is our port, maybe, and we have, I don't know, some passenger ship. You can see there's a person on it, right? They're going this way. We can maybe have some tanker, which is going to be a big long ship, right? I don't know, maybe it looks like that. I don't know what tankers look like, but we'll say it looks sort of like that. It's going this way, right? And we can ask a question, right? Say at some given time, right? Say at some given time, right? The ship is 40 miles from port, right? And it's sailing at 30 miles an hour, okay? And then the tanker um, is 30 miles from port, and it's sailing at 20 miles an hour, okay? And we can ask the question, right? How fast is this changing? Right, the length of this line. And this is a related rates problem. Let's put some labels on this, right? Maybe we label this side of the triangle X, this side of the triangle Y, and then, naturally make the hypotenuse Z. But here's the crucial thing to notice here. 20 miles an hour, that's the rate that X is changing with respect to time, right? 30 miles an hour, that's dy dt, okay? And, right, here's the other thing we know, right? That x squared plus y squared equals z squared, right? Good old-fashioned Pythagoras. This allows us, of course, to solve for z at this given time, right? You can sort of go through the math. This is going to be 50 miles between them, right? Because this is a 3, 4, 5 triangle, okay? But if we want to find dz dt, right? Notice that the speed with which this line is changing, that's dz dt, right? If we want to find that, well, we can take the derivative of this guy with respect to time. That's going to give us 2x x prime plus 2y y prime equals 2z z prime, right? Where, of course, x prime is dx dt, y prime is dy dt, and so on. But then from here, right, we can, divide by 2 to get rid of these 2's. And then now it's just sort of rearranging and plugging our stuff in, right? Z prime is going to be x prime plus y prime over z, right, which is going to be 30 times 20 plus 40 times 30 over 50. And if you run this calculation by hand, wouldn't you know it, you get 36, right? So that means that the distance between the ships is moving apart at exactly 36 miles per hour, right? That's sort of the power of these related rate situations, right? It allows you to sort of, look at how quantities are changing in more real world environments where you have, more than one variable and they're all changing with respect to time. All right, so that's going to cover it for this part. If this related rate stuff is still a little bit confusing, that's totally okay. This is one of the stranger concepts, I think, for a lot of first-time calculus students. The biggest advice that I can give you, right, is if there's any sort of model, like draw a picture and label everything you know, right? That was what sort of allowed us to get this, right. If I had just read to you, 2 ships leave port, the one going north is 40 miles away from port and traveling at 30 miles, blah, like you wouldn't be able to actually figure this out, or at least it would be much more difficult. But the moment that you start drawing pictures and start seeing the geometric relationship, you can grab Pythagoras, you can realize that this speed is dx dt, and so on. Okay, so definitely draw pictures for related rates whenever you can. that's going to wrap it up for this part. Come back in the next one and we'll talk about one more sort of subtle way that we can use derivatives.